All right, welcome back. Our discussion on motion continues. So you can see from our little series of bullets here, we've gone over what distance, position, and displacement are in terms of what distinguishes their differences. We've looked at differences in speed, velocity. Today we're going to focus on acceleration. We've talked about the difference between vectors and scalars, about adding, subtracting vectors a little bit, and we're going to focus a little bit more on our motion information from position time, velocity time, and then eventually acceleration time graphs. So we got a busy day. So quick recap of types of motion. So these are all position time graphs. It's very important to make sure you recognize what type of graph it is. So the first one here is an object that is not moving, because you can see this position is not changing. It's constant as time ticks away. So that is an object that is staying put. The blue line here is an object that is moving away. You can see this distance, or this position here is getting larger. So it's getting farther from zero, so that is moving away. And then we also explored that the slope of this line, the rate of change of that line, if you look at that as 5 meters in 5 seconds, which would be 5 meters per second. Sorry, 1 meter per second, pardon me. And that slope of a position time graph is the rate of change of the position time, which we call velocity or speed. We'll call it velocity. Okay, and then we have the green one down here. You can see this position here is getting smaller. So this again is a moving object, but this time it's moving toward the reference point. And again, you could find the slope of that line. Just make sure you don't use the 10. You have to use the difference, or the change. So the change is negative 5 meters over 5 seconds. So we would get negative 1 meter per second. Okay, that's a quick recap of position time graphs. So the key pieces there are the direction of the object moving, either away or toward, and the slope of the line is the velocity of the object. All right, so we also have been talking about uniform motion. So we also have non-uniform motion. So if you look at this object here, it's a nice little curve. So this is an object that is moving away from the reference point, and you can see that as these positions get larger and larger. But it's not doing it in a constant fashion. So I'm just trying to erase my ink here. Let's use the brush. And because it's a curve, there's no one slope that we can draw. What we can see, though, and we'll expand on this thought a little bit more as we move along, is we could put little slopes on different points. And if you were to look at all of those little slopes, you would see they are progressively getting bigger. And I'm just going to make up some numbers to help you see that. So these slopes, which are also our velocities, are getting larger or steeper. Okay, so if my velocities are increasing like that, that would imply that I am accelerating. And that's going to be one of our focuses today, is on acceleration. So when you see a position time graph that has a curve, that's going to tell you it's non-uniform motion or accelerated motion. So let's jump right in. Velocity is the change in position over time. So we have 5 meters per second, 30 kilometers an hour. Acceleration is the change in velocity over time. Okay, so velocity is the change in position. Acceleration is the change in velocity. Okay, so you'll notice we can have 3 meters per second per second. We can have 5 kilometers per hour per second. Okay, and we'll explore this a bit more right now. If the time units for acceleration are the same, we tend to write the time values squared. So you might see something like this. Okay, so 2 meters per second squared. What that means is you're changing something like this, 4 meters per second per second. Okay, and again, sometimes it's easier to write that one to understand what's going on while we're learning. And this is what it would look like. So at T1, I'll change colors here. If I started from rest, I have a velocity of 0. After 1 second, because I'm accelerating at 4 meters per second, let me get rid of this guy so there's no confusion, I would now have increased my velocity by 4 meters per second. After 2 seconds, I've increased my velocity by another 4 meters per second, so it jumps up to 8. At 3 seconds, I've increased my velocity by another 4. I'm now up to 12 meters per second. Okay, so that's an example of acceleration. We could also do this with some slightly different units. We could have 5 kilometers per hour per second. Okay. Oops, I know this should be a 5 here. My apologies. So if we started from, say, 10 kilometers an hour, that was our initial velocity. After 1 second, I would have to increase by 5 kilometers per hour. After the second, that's hard to say, I would have to do another 5 kilometers per hour increase. And then lastly, another 5. Okay, so you can see how my velocity is increasing with time. That is what we call acceleration. Okay, so when we look at these types of things, this one, the first example here, makes a lot of sense. Okay, so case 1, velocity and acceleration are both in the same direction. So if you imagine you're standing in a hallway and you decide to sprint down the hallway. Okay, so as you start moving your legs, you're going to be accelerating and your velocity is going to be increasing. Okay, so you will be moving, say, away from your reference point. That's what this position time graph here is. We're moving away from our reference point, and we're doing it in a non-uniform fashion because I have a nice curve, which means I'm accelerating. And again, I'll go back to these little, if I draw these little lines on here, these little tangents, we'll discuss that word shortly. Okay, you can see that these guys would get steeper and steeper and steeper, and if these represent velocities, you can see that they're increasing. Okay. Now, the next one is the one that's a little bit tricky for people. You do it all the time, but you may not have thought about it mathematically, okay, or at least in terms of vectors. So this is case 2 is the velocity and the acceleration are in the opposite directions. Okay, so the object can continue to move forward. So you can see this displacement here is still getting larger, but you can see it's not getting larger as quickly. Okay, this is the situation where we are slowing down. Okay, so you can have an acceleration that opposes your velocity, and it means you're accelerating in the opposite direction, and that's going to decrease or take away from your velocity. Okay, so it means you're going to slow down until you reach 0, and then you have to figure out if you're going to go back the other way or if you've just come to a stop. Okay, so this is the slowing down case. It seems really obvious when we talk about it right now, but there will be questions where it just will bug you that you're accelerating in the opposite direction of your velocity, and that will be really tricky on your mind. So just be mindful of case 2. This is a really tricky one. Case 3 and 4, these are the exact same things as case 1 and 2. The only difference is instead of moving in a positive direction, we're moving into a negative position from our reference point. So I won't go through all of those again. But basically you have acceleration, velocity in the same direction, acceleration and velocity in opposite directions, and again, it's a slowing down case. Okay, so confusing words in science and day-to-day living. So when an object is experiencing both acceleration and velocity in the same direction, we say the object is speeding up or accelerating, and we're generally pretty happy with that. When an object is experiencing acceleration in the opposite direction of its velocity, okay, this is the case for slowing down, or what we sometimes say is decelerating. Okay, so decelerating implies that the acceleration is in the opposite direction than the velocity. That's an important distinction to know. But the object is still in fact accelerating. Okay, so if we look at a model rocket, so if we launch a model rocket into the air, most people would describe it something like this. Let's just close this off. They'll say the rocket decelerates until it stops at its highest point, and then it accelerates back to Earth. And it's not entirely wrong. It's just sometimes a bit confusing on what that means in terms of numbers and directions. So the rocket is always accelerating in this case, and it's always accelerating towards the Earth. Okay, so, and I'm applying a model rocket that doesn't have a constant jet. We just launch it in the air, and that's the only impetus to make it move. Okay, so when we look at something like this, once it's launched into the air, okay, by slingshot, by whatever we're using to launch our model rocket, it will have an initial velocity, okay, and it will go speeding up into the air. It will eventually reach its maximum height, and it will actually stop. Not for very long, but it'll stop very briefly, and then it will start to fall back down to Earth. And again, the green represents velocity. What you can see in here, though, is this purple vector represents acceleration. Okay, up here, acceleration. And you'll notice that purple vector didn't change throughout the entire problem. Okay, that is because once we throw an object in the air or we project it into the air, it is always accelerating towards Earth. Okay, so the decelerating part implies that there's some sort of change, when in fact this entire trip for this thrown model rocket or tennis ball or football, whatever it might be, the acceleration is always down towards Earth. Okay, and it's only there are different cases. This is a case 1 here, where the velocity and the acceleration are in opposite directions. So this is your slowing down. Okay, at the top, it's not moving, so we'll leave that one out. And then this is case 2, this is case 1, where acceleration and velocity are in the same direction. So it's actually speeding up as it comes back down to Earth. Okay, and we'll keep working on that. That's a tricky thought. All right, so position time graphs. A position time graph plots the position of a moving object with respect to time. The rate of change, that's a fancy word or a couple words for slope. The slope of a position time graph is velocity. Now, we have something called a velocity time graph. A velocity time graph plots the velocity of a moving object with respect to time. So instead of plotting position, we're going to plot the velocity. The rate of change of a velocity time graph is acceleration. Okay, so it looks like that, and you'll recognize all those formulas from the position time and velocity time graphs. Those are just slope formulas. That's all they are. Okay, so if we have this example down below, notice this is a velocity time graph. So when we look at this, I have the red triangle marked out to calculate the slope. So we have a run of 10 seconds. We have a rise going from 0 up to 30. We have a rise of 30 meters per second. So when you do your slope or your rate of change, you would have 30 meters per second over 10 seconds. Okay, and then if you did that division, you would come up with 3 meters per second squared, which is a unit for acceleration. All right, so there's a couple to practice. You've got a formula on the top here. You can pause it and then go through them, and then we'll reveal the answers. Okay, let's have a quick look now. We're all back. A catapult accelerates a rock from rest. Okay, so from rest means something. That means our initial velocity is 0 to a velocity of 15 meters per second over a time interval of 12.5 seconds. So if we look at our average acceleration, we have a change of 15 meters per second happening in 12.5 seconds. So we do that quick division and we get 1 point something. 15 divided by 12.5, 1.2 meters per second squared. Okay? Bring that up a bit in case you couldn't see the last question. As a car approaches a highway on-ramp, it increases its velocity from 17 to 25 over 12 seconds. So again, we could do this 25 minus 17, that's the change, and it's happening over 12 seconds. So 8 divided by 12, 0.67 meters per second squared. Looks like that. And then lastly, a squash ball with an initial velocity of 25 meters per second west is hit by a squash racket, changing its velocity to 29 meters per second to the east. Now this is a tricky question because the change in velocity, okay, is not 4. the change in velocity, because they're going in opposite directions, is actually 25 minus negative 29, if you want to think of it that way. And all of that's going to happen in 0.25 of a second. So we actually have 54 divided by 0.25. We have an acceleration of 216 meters per second squared. Okay, and that's a really large number, but what you have to remember is the time it's actually accelerating is very small. Okay, and that's one of those kind of weird things that shows up with acceleration, but you do get some fun answers. If you hit a volleyball and we'll talk about that later. All right, so using the velocity time graph to determine the displacement of an object. Okay, so if an object moved at 4 meters per second for 5 seconds, it would travel a distance of 20 meters. Okay? The object above has different velocities. Okay, so this object in the graph here has different velocities at different times. So because that's changing, we have to do a little thinking a little differently. We determine the distance traveled by, and there's two ways to do this, finding the average velocity. Okay, so if you look here, this object started with 0 meters per second. It finished at 30 meters per second. So the average velocity, 30 plus 0 all over 2, the average velocity should be 15 meters per second. Okay, and that would be one way we can sort of track this problem. The second way is we can find the area underneath the given graph. Okay, and that's the way I find tends to be a little bit easier to manage. So if we have this, I'm going to grab this little triangle here. You can see I've already changed colors, and I bring this down. So I've essentially cut the top part off, and I have made, whoops, get in there. I have made a large rectangle. Okay, which makes it easier to find the area. Now if you notice, when I cut that triangle off, lo and behold, I landed at 15, which was the average. So the area under this curve is 15 times 10, or 150 would be the number. Now the question now is, what is the units? Well, if you multiply a meters per second times a second, which is what we've done, the 15 is meters per second, the 10 is 10 seconds, you end up with meters. So even though we're finding an area, don't panic, the answer here is 150 meters. That's how far the object's position has changed. Okay, so those are two ways. That's one way. We can do the triangle and recreate. We can find the area under the curve. And then lastly, finding the distance traveled by using the area under the curve only works with velocity time graphs, not position time graphs. So the area idea here, it only works with velocity time graphs, and we'll emphasize that more tomorrow in tomorrow's lesson. So let's try one. What is the displacement represented by the graph in figure 4 over the time interval from 0 seconds to 10 seconds? So if we look at this, the first thing we should notice is it's a velocity time graph. Okay, so over the first 5 seconds, this object's velocity is changing. Okay, so that's important to note. And then over the next 5 seconds, the velocity is constant. So if we go after the change in position, the displacement of this object using the area technique, we need to find the area of these two shapes. Okay, so this area here has a height of 10 meters per second, has a width or a base of 5, but because it's a triangle, we have to divide by 2. So we get 25 meters for the first block. The second block, this is an area of a rectangle. It has a height of 10 meters. It has a base of 5 meters. So this has, 5 seconds. So this has a total area of 50 meters. So the total displacement, change that to displacement, would be the 25 meters plus the 50 meters for 75 meters total. Okay, so you're just finding the area under the curve on a velocity time graph. Okay, A little advanced practice just to clarify a few things. I said the word tangent already, so we should define a little bit more what that is. A tangent is a line that contacts a curve at one point and one point only. A secant is a line that contacts a curve at least 2 points, usually just 2 points is all we're interested in. So tangent 1 point, secant 2 points. Your average velocity, as we're going to see, is the change in position over the change in time. It's represented by a secant line. Okay, and sometimes we'll call this arc, and it stands for average rate of change. You'll definitely see that in grade 12 math, but we can introduce the concept now. Instantaneous rate of change is the change in position at a specific instance in time. Okay, it's at one singular dot. We model that with a tangent, and I'm going to show you what they look like in a second, and that'll hopefully help clarify that point. And now this looks really busy. Don't panic. Okay, so we have some position of a water-powered rocket that's fired up in the air. All of its data can be modeled with this little expression at the top here. And I've generated a table of values for you. Okay, we don't really need the equation so much. We just need to look at the graph. If I find the average rate of change, if I find the slope between these 2 points in green, okay, I'll come down here. That's this green line right here. You could see that green line is very close to the purple of the graph. So it's actually a fairly close representation. And if we found that average rate of change and we just went 15 minus 0 over 1 minus 0, we would get 15 meters per second as the average velocity from 0 to 1 second of this rocket. If we ask for the velocity, so that's green out of the way. If we asked what is the average velocity from 0 to 2 seconds, so say we take a larger interval, and I'll just use the red marker here, from 0 to 2 seconds. So again, I'm going to use the slope formula, and I'm going to go 20 minus 0 over 2 minus 0, and that's where the 10 comes from. But you'll notice on this line right here, it isn't that close to the purple anymore. It's quite a long ways away. And what you'll notice with our answer, it now says we're traveling at 10 meters per second, which is very different from the original 15 meters per second we found over the first second. If I do a larger interval from 0 to 3, now you can see I'm missing an awful lot of my graph. I'm missing all of this piece of my graph. Okay, if I do the same slope calculation, okay, what I find is I get 5 meters per second for the blue line. And then lastly, and I didn't draw it in here, but if I go from 0 to 4 and I find that slope, that's this guy right here, my average velocity over 0 to 4 seconds would be 0 meters per second. That means my average velocity is 0, means I didn't move. Yet we can clearly see in this graph that the object was launched into the air, flew up high, and came back down. So what we have to be very careful about when we're working with average velocities or average anythings is the intervals that we investigate need to be appropriate or small. If you try and do an average over too large an interval, you get ridiculous answers like 0. Okay, so when we do this, for this one here, 0 to 1 would be good. That's a reasonable interval, and it would be an acceptable answer. Okay, so let's carry on with that thought. Try and wrap this up as quickly as I can for you. Same problem. Okay, so we don't have to regenerate any of those numbers. Only we're going to look at slightly different intervals. So what is the average velocity from 0 to 1? Okay, that's green. I did that on the previous slide, and we knew that this one here, this is 15 meters per second. That's the slope of that green line. If I found the average velocity from 1 to 2 seconds, so that's this interval up here, we would find that it's 5 meters per second. Okay, so there's this change. This object we know is slowing down. It's going up in the air. It's eventually going to stop and then come back down to the Earth. So we can see from here it went from 15 meters per second. It slowed down to 5 meters per second. And those are just averages, though, over those relatively large time intervals. Now, this is where it gets really interesting. What is the average velocity from 1 second to 1.5 seconds? So that is looking from here to here. Okay, and I'm not going to do all the calculations just for the interest of speed, but you can see there's a blue line right in there. Well, the slope of that blue line is 7.5 meters per second. Okay, if we carry on using smaller and smaller intervals from 1 to 1.1, again, and all we're doing is slope calculations. I guess I could have used orange for that color, sorry. Then we end up here with 9.5 seconds. As we move even smaller, from 1 to 1.01, eventually we come up with something like this. We would have a slope of 10 meters per second. You can see in here I have progressively smaller drawings, but they're beyond the scope of the software for me to draw upon. And they get smaller and smaller. I'm moving my secant closer to a tangent. Now, we can't calculate a tangent yet with our current mathematics. If you carry on in calculus, you can totally do that. But what we can do, and I'm just going to try and clear off some of this information, is we can use a non-calculus approach. We can use a manual approach. So if I drag this in, if I look at 1 second, this is where I'm trying to find out the instantaneous velocity right there. If I take my ruler and I draw a tangent, which is a line that contacts the curve at one location, and then I use the grid that's in behind to determine the slope of that tangent, you can see I have changed from 5 to 25. So there's a rise of 20 meters. And if I take my run, this is 20 meters, my run would be going from 0 to 2. This is 2 seconds. I would have a slope of 10 meters per second. This right here is the instantaneous velocity at that location. Now, if you picked another location anywhere else on this graph, say here, it would have its own tangent line. You'd have to recalculate everything, and you would get a new instantaneous velocity. Okay, so instantaneous is simply at a point. Average is between 2 points. Okay, averages tend to smooth out some of the irregularities. Instantaneous will tell you exactly what's happening at that location. Okay, now that's pretty heavy for today, so if you followed that, that's awesome. We'll carry on with that discussion though. This is, let's see if I can fit it all in here, page 30, 2, 4, 6, 8, 9, if you could give those a try. 9, or if you want to try 11 as well, 11's quite fun. This is the one where you need the instantaneous velocity on. But thanks for tuning in. Appreciate that. Good luck.